invented in particle physics, but have also applications in nuclear physics. Now, in the lectures, emphasis will be laid on the experimental test of the symmetry concepts. In this sense, can we see in experimental data effects of these symmetries? So the lectures are based on a book which I wrote with Piet and Alejandro Frank, which probably you can download in your university because it's a Springer book. At least at the University of Cologne you can download the complete book for free. And so if you would like to have the reference, then you have to use this link, which I leave you some time to write it down if you want, and you can try then to get the complete e-book as a download. Secondly, I would like to mention two other books. The first one is by Iacello and Arima. It's called The Interacting Boson Model, and it concerns the lectures of today, except that the neutron-proton version of the interacting boson model will be treated tomorrow by Norbert Pietrala. The second one is again a book of Piet and Franco Iacello, and it's called The Interacting Boson Fermion Model, and it deals with the lectures I will give on Friday. So if you want to take a look during the coffee break, the books are here, and so you can also take the coordinates of the books. So, why symmetries are important? Now, let's start with classical physics. In classical physics, if you have a closed system, and that's denoted by this square, and in this closed system, that's no interactions with the environment, you want to formulate physical laws. Then you would like to formulate them such that if you make a just displacement in space of this closed system and the laws, then you would like that the laws don't change. It would be very complicated if every place you have to redefine physical laws again. And because of this property, we have the conservation of momentum, P. At the same time, we would like that the physical laws which are valid now were also valid at the beginning of the universe, or are valid in 1 billion years after we are living here. So it means that we would like to have an invariance over time displacement. This leads to the conservation of energy, A. And finally, if you have the physical system and you let it rotate in space, then you would like that the physical laws don't change. This leads to the conservation of angular momentum, L. And if you think about your physics course, classical mechanics and all classical physics, then the conservation of momentum, the conservation of energy, and the conservation of angular momentum are in some sense the basis in order to make the description of our material world. So this shows in classical physics that symmetries are very important. It facilitates our description of the universe. Now, the question is, are there more constants of motion like energy, momentum, angular momentum? And we go over to quantum mechanics, and the first real success of quantum mechanics was Niels Bohr's description of the hydrogen atom in 1913. Now, if you look at the solution of Bohr's description, which by the way is completely wrong, but nevertheless the answers were right and were in agreement with experimental facts, then if you look at this description of the hydrogen atom, then in essence you have a very simple formula. It says the energy of a state is given by the main quantum number n, the angular momentum L and its projection m, and this energy is equal to a physical constant, the Rydberg constant, divided by the main quantum number squared. So that's what Niels Bohr found out, and that agrees very well with experiments. Now let's consider a little bit more. What does this say? N is also a conserved quantity, or a constant of motion, which is independent of the value of this constant. Yeah? So you can have another value for this constant, you will have the same n. Wave functions do not depend on the value of this constant. So the wave functions are independent of this proportionality value. And finally, n gives us which values of L we can have, and L in turn gives us which values of M we can have. So it means we have kind of what is called quantum numbers, which are N, L and M, and so there are relations between the upper quantum number, which is the main quantum number N, and L, and then between L and N. Now, only 20 years later, the brilliant Russian physicist Vladimir Fock, which by the way is also the inventor of the second quantization, in 1934 found out that the equations of the hydrogen atom are invariant under orthogonal rotations in 4 dimensions. O4, like O3 is for orthogonal rotations in 3 dimensions, and they exhibit a dynamical symmetry. And that we will study in a first instance, and that will be very important for the rest of the course, a dynamical symmetry. Now, symmetries are associated with groups, and so the relation between Lie groups and quantum mechanics is quite important, and so we want to study this a little bit more. What is a Lie group? If I do a rotation, yeah, then I can do an infinite number of different rotations. Yeah? And this is described by Lie groups because these are what is called continuous groups. It means you can do a continuous movement of rotations with an infinite number of elements. So I have infinite number of rotations I can make. And so we start with this example which is common to us, rotations in 3 dimensions which form the Lie group SO3. Now, associated to this infinite number of rotations, there is an algebra. And the algebra has a limited number of elements. So let's illustrate this. So associated to the Lie group is a Lie algebra with a limited number of called generators, JK, that generate the rotation alpha via exponentiation. Let's take as a first example rotations in 2 dimensions. Yeah? So I have here x, y, z, and then I can turn the z-axis, changing the x and the y axis, and do this rotation over an angle alpha. Now, in order to generate such a rotation, we can apply the exponentiation of the Lz operator. So the z component of the angular momentum. So Lz explicit in quantum mechanics is given here as minus E h bar x d di minus epsilon d dx. And so if I do this rotation, I can generate any 2-dimensional rotation by just changing the angle alpha and applying this generator. So we conclude that if you have a rotation in 2 dimensions, there is only one generator in the algebra, which is the Lz operator. So although I can make an infinite number of rotations in 2 dimensions, which forms the group, the algebra itself has only one element, one generator, Lz. And now Piet probably has illustrated it in his course. If you do now rotations in 3 dimensions, then you have to do a rotation around the z-axis, a rotation around the x-axis, and a rotation around the epsilon axis. And you can generate any rotation in 3 dimensions by applying Lx, Ly, and Lz, the 3 components of the angular momentum operator. Or, if you write it as a scalar product, then you have here, because the rotations have also an x component, an y component, and a z component, you have the scalar product between alpha, defining the angle of the rotation, and the angular momentum. So we conclude that while for SO2 we had only 1 generator, for SO3, rotations in 3 dimensions, we need 3 generators of the group, of the algebra, and they are the x, y, and z component of the angular momentum. Now, generally, of course, you would like to have a mathematical definition, and this was done by Sophus Lie. A set of generators define a line Lie algebra if they close under commutation. That means if you take 2 generators, you take the commutator, you can write it as a linear set of the other generators. So this is what is denoted here. Is there a laser pointer in this?
Yeah, that's
yeah. So this is what is denoted here. If I take the commutator of 2 generators, then I can write it as a linear combination of the other generators. And these constants are called the structure constants, or the Lie structure constants. So that's an important property. And on the other hand, they have to fulfill the Jacobi identity, which is again a combination of commutators. So we have the commutator of kk with the commutator of the other 2, and then you have a cyclic, you see m moves here to the first place, and then L moves here to the first place in the third one, and this has to be 0. So as an example you know very well, is the angular momentum operators, which are the generators of the SO3 algebra. So if you take the commutator of Lx and Ly, then you get something which is Lz, Ly, Lz, then you get Lx, Lz, Lx, then you get something which is proportional, linear to Ly. You have seen also in quantum mechanics that there are more examples. These are the orbital angular momentum operators, but also the spin angular momentum operators. They fulfill the same commutation rules. And because spin operators and orbital operators commute, you can now sum the orbital angular momentum and the spin angular momentum to get the total angular momentum, and again you get the same commutation rules. So these are 3 examples of this angular momentum, spin angular momentum and total angular momentum operators. Now, the next thing I would like to introduce are Casimir operators. They were invented by Hendrik Casimir, who quit science to become one of the directors of Philips in industry, which made Pauli very mad. He always called him Herr Director. So Casimir found out that for any Lie algebra there are operators which are constructed out of the generators. This is important. So the operators are constructed out of the generators of the algebra, and which have the property that they commute with all generators. So the commutator of this operator constructed out of these GKs is equal to 0. And the operators, these Casimir operators, can be of first order, it means a linear combination, of second order, which means a quadratic, of third order, which is a cubic combination of generators. Now, let's start first with rotations in 2 dimensions. There is one generator, which is Lz. And of course, trivially, Lz commutes with itself. Yeah? Lz, commutator with Lz, is 0. So it means the Casimir operator of SO2 is Lz as a linear Casimir operator. So we find that we have Lz as a Casimir operator of SO2. In SO3, it is the length of the angular momentum operator. So L square. So if you do a rotation, L square doesn't change its value. And in fact, you can prove that L square commutator with Lx, Ly, and Lz is equal to 0. So this is then the Casimir operator. It's a Casimir operator of second order of the group SO3. There is no Casimir operator of first order for the group SO3, and so we conclude that L square is this Casimir operator. For SO2, which is the algebra associated with spin, it's S squared. So the length of the spin angular momentum. And also here you can prove that S squared with Sx, Xy, and Sz is commutator is equal to 0. And so we conclude that the Casimir operator of SO2 is the S squared operator. And so for any Lie group, you can find this kind of Casimir operator.
Excuse me.
Yeah.
So could you go back to the answer? So yeah. First question is, what is the meaning of out of the generator GK? The first line.
The last line?
Yeah. First line can be constructed out of the generators.
Yeah, the Casimir operator has to be constructed out of the generators. For instance, if you have L squared, then it's Lx squared plus Ly squared plus Lz squared. Yeah?
Yes.
So the Casimir operator, it cannot be, you could take any scalar, yeah? That would commute with all generators, but that has no sense. It has to be constructed out of the generators itself.
So it seems there are many Casimir operators.
Yes, there are several.
Commute with generator.
Yeah. But we will generally restrict to Casimir operators up to the second order. Yeah, only two body interactions, so to say. Yeah. But there are. This is a question of mathematics. Many of the things here are questions of mathematics, yeah? And they are solved for once and forever. So there are general procedures how to construct the Casimir operators. Yeah?
But in SO2,
Yeah?
LZ include.
There's only one generator, Lz. So if you have to make a Casimir operator, it has to include Lz. And it's trivial that Lz commutes with itself.
Yes.
Yeah? And so it turns out that this is a Casimir operator. Now, in order to make a connection with things you know, if you, we will come to that, but if you know, if you apply Lz to a wave function, you will get M, magnetic projection. And if you apply L squared to a wave function, you will get L plus 1. So these are then eigenvalues, and they are constants. We will see why soon.
So for AC2 symmetry, Sx will be commutated with Sx, right? So Sx would be again one Casimir operator.
S squared is again a Casimir.
I just want to know if Sx is always the Casimir operator. Sx.
No, because if we return, then we see that Sx with Sy gives Sz. It doesn't give S0.
But if Sx we just commute with Sx again, that is the case for Lz.
No, you see, while we could have the linear one for Lz in SO2, because there's only one generator, in SO3 there are no linear possibilities. Because always the commutator is not equal to 0. It always gives one of the other generators. It's only the length of the angular momentum or the length of the spin angular momentum which is conserved. So I cannot, unfortunately, then you have to come to the University of Köln and follow my course in winter semester, then I can prove everything in detail, but there is no time at the moment. Yeah? So the course starts 7th of October. Vasilable, probably. So these are the special operators. But now I would like to go to another point. It's a simplified picture, but I just want you to grasp the idea. Don't go in detail. Mathematically, it's not all completely correct. But in order to get an idea why symmetries are important, we have to make some ideas about Hilbert spaces and unitary transformations. So to introduce the approach, and I will also use an S and D boson system, which is in fact in boson model basis. So consider that we have n S and D boson and a wave function. So we can now, in second quantization, we can work on the vacuum, which is here, and then we have the creation operators of D boson with a magnetic quantum number +2, +1, 0, -1, and -2, and of course an S boson is an L equal 0, D is L equal 2, and so it has only a projection 0. Now, if we make our wave function out of these creation operators, then we have ns times the S boson creation, nd, and so on. And we need some normalization factor. Now we can consider the wave function to be a vector in a 6-dimensional space. So the space is spanned by these different magnetic substates of the boson operators. Yeah? And this 6-dimensional complex space we call the space spanned by S and D bosons. So this means we can write this 6-dimensional vector, and we can put here how many S bosons, D, -2, and so on we have. Now suppose we change the basis to another one, which of course we can always do. Then we have here our original vector, 6-dimensional. We have a matrix which is a 6x6 matrix, and then we have now our changed number because of the changed basis. Now here there are 36 matrix elements. 36 matrix elements in this matrix. Now, for wave functions, we impose that the norm should be a constant. Yeah? So the norm of this vector is then this and the transposed and the product of both. Yeah? So if you write it explicitly, then you have here the annihilation operators, and here you have the creation operators, and you have this normalization factor. But that should happen also if we do a change of basis. So this imposes on the matrix of the change of basis, big 36 element 6x6 matrix, which I denote by A, that the transposed product with the matrix itself should be the identity. Yeah? If this is valued, then I can here use A times the new basis and the new norm that makes this matrix out. And so if you do it explicitly, it means that the sum over J of complex conjugate matrix element AGI multiplying with the normal AGK has to be equal to delta EK for every E and K going from 1 to N. So now the N square conditions which result from this relation, yeah, N squared conditions, because we have E and K can be 1 to N, and we have, these were complex matrix elements, so we have 2n squared real parameters in our matrix. One real parameter describing the real part, and one real parameter multiplied with I describing the complex part of our matrix. So we get in total n squared free parameters. Yeah? So we have 2n squared real parameters, we have n squared conditions because of this property that the norm should be conserved. And so the set of n times n matrices fulfilling the conditions forms a realization of the unitary group Un. In our case, n is equal to 6, U6. And more specific, the group Un is called the n squared parameter Lie group or the n squared order Lie group. In the case of our S and D boson space, the matrices form the group U6. We can impose one more condition, that the determinant of A has to be equal to 1, and then one speaks about this special unitary group, and this is denoted with SUN. And of course, one more condition makes it an n squared minus 1 order Lie group. Now, we can continue, and we have our unitary matrices, so the matrices which have this property. Now we can look for subsets of these matrices which have other properties. And one important subset is, suppose we now do not mix in our basis transformation S and D bosons. So we make matrices which have here zeros and here zeros, such that the number of S bosons is conserved and the number of D bosons is also conserved. But the D bosons can transform between the magnetic substates. Now, instead of having now 36 complex numbers, we now have here 1, and here we have 25. So it's clear that this class of matrices forms a subset of the other class of matrices. And this, in group theoretical language, makes that this class of matrices is a subgroup of the original class of matrices. And because we have 5 times 5, in fact, the subgroup for the D bosons among themselves is U5. Here we had U6 because we had D and S boson, L equal 2 and L equals 0. And now here we have separately L equals 0 and L equal 2. Finally, we can now continue and make other subclasses of matrices. Now here we had complex numbers. Yeah? These matrix elements can have complex values. Now, if we impose that we only take those matrices which have real numbers, that's very clearly a subset of the original matrices which has complex numbers. Now, our condition here, Ji complex conjugate, Jk, because the complex conjugate is equal for a real number to the real number itself, it becomes now Rji, Jk is equal to delta Ik. Now, because of this symmetry property, because now I can change Ji and Ejk like that, it's the same thing. It was not the same thing here because we had a complex conjugate. Yeah? But now it becomes the same thing. And that means that the number of conditions due to this request that the numbers are real is different. So we can take the diagonal elements, Jj, Jj. These are n of them. And then we have n times n minus 1 divided by 2 because of the symmetry property conditions for the off-diagonal elements. And now we see we have a different number of conditions equal to that on our n squared parameters, not anymore 2n squared, because the numbers have to be real. There are only n squared parameters. And if you do the calculation, very simple calculation, you find out that these matrices which have this condition, they form an n times n minus 1 divided by 2 order D group. And those are denoted by the symbol ON or SON. And so we find that if we started from the transformation matrices for S and D bosons, then we had a unitary in 6 dimension group. We had a subgroup which is U5. We can just leave this out here. And then we find that there is also a subset of matrices which are fulfilling the SO5 symmetry. It turns out that we can continue this and find out that we end up with an SO3 symmetry. But now, why are symmetries so important in quantum mechanics? Now, suppose we have a Hamiltonian which commutes with generators of a group G. Yeah? It means that this Hamiltonian is constructed out of Casimir operators. So if the Hamiltonian commutes with the generators, it is said to have the Lie algebra G, or to be invariant under this Lie algebra G. Now, what does it mean? It means that if I take any generator from this algebra and I have a solution, this is a Hamiltonian, I have a solution with an eigenvalue of the Hamiltonian, and I now operate with the generator GK on this solution, then because of the commutation rules, I can change the sequence. Because this was a solution of this Hamiltonian, it has an energy eigenvalue and the wave function again. And now GK is working on a scalar, so it means I can again change the sequence of the energy. Energy is a scalar, and so I obtain here then GK on gamma. And so if we now look at the total, then we see if I have a gamma solution with an energy A, then for all generators I can construct other solutions having the same energy. So all these states are degenerate, all have the same energy. And I can construct as many as I have generators. But that means that I can classify the energy as belonging to a certain quantum number, gamma, and I can classify the degenerate states by another quantum number, gamma small, by just to classify these different states. And if I work on such wave functions, then the generators can only change the value of small gamma, but they cannot change the value of big gamma, because big gamma is classifying the energy. So it means they can not get out of this big gamma, they just can change the small gamma. Now that's very important. It will become important afterwards. In the language of group, I will come to that. As I said, my prologue is rather long. Now, suppose now that we can find or construct by linear combinations a subset of generators. So from the original set of generators, GK, we can now select a subset of them belonging to this original set, and they also fulfill the Lie algebra condition. So they commute among themselves, or one says they close on the commutation. Now, They are then the generators of a Lie subalgebra G prime, being part of the larger algebra G. And associated with that, there is a subgroup of transformations which has the same G prime definition. Remember, generators, finite number, generate an infinite number of rotations in an abstract space of any dimension. Now, as I said, for every Lie algebra, there are Casimir operators. Now, we can construct now the Casimir operators of a certain order n prime of this subalgebra. And it has a property that it commutes with all generators of the subalgebra. However, it doesn't commute with all generators of the original algebra. Yeah? The Casimir operator, if I apply it and I take one of the generators of the original algebra, which is not a part of the subalgebra, there is no guarantee that it commutes. However, the important point is all operators of the subalgebra do commute with the Casimir operator of the original algebra. So that's an important point. Consider now that we have an Hamiltonian, which is the Casimir operator of the original algebra, with which all operators commute, and the Casimir operator of the subalgebra, with which only a part of the original generators commute. Then we have that the Hamiltonian commutes with all generators of the subalgebra, and that means that where we had gamma and small gamma, now we can have even an additional quantum number, because if I apply this to an eigenstate, I will get a degenerate eigenstate having the same energy, but only for part of the subalgebra. So now I have three quantum numbers, alpha, beta, gamma. And one has that the Hamiltonian working on alpha, beta, gamma state, being A, the Casimir operator, which does not allow to change alpha, so which defines the energy as a function of alpha, and we have the Casimir operator of this subgroup, which cannot change beta. And so we now obtain that the analytic solution of such a Hamiltonian is A times the energy as a function of alpha, alpha, beta, gamma, plus B, the energy as a function of beta, of alpha, beta, gamma.
Excuse me.
The addition of the Casimir operator of the subgroup cannot break the original symmetry. That's the essential point. The original alpha quantum number is conserved. Yeah.
So small gamma
Yeah.
is a quantum number associated with
The subalgebra. The degeneracy of the subalgebra. Because this holds for a subset. Yeah? So it means, let's say I have 36 generators in the beginning, and I go to a subset of 25. Then if I have one solution with an energy, if I apply 25 times this generator on this solution, I will always get another solution with the same energy. So I will get a 25 degenerate state. And so in order to classify that, the small gamma from before, which is now replaced by the beta, yeah, by the beta, we have an additional label describing the degeneracy of the subalgebra. So before I had two quantum numbers, one describing the energy, one describing the degeneracy. Now I have three, one describing the original energy, one describing the energy due to the subalgebra, and one describing the final degeneracy, alpha, beta, gamma. The energies depends on alpha, on beta, and the degeneracy is classified by gamma. Think of, we come to a concrete example.
Excuse me.
Yeah.
I have a question. Before you said that actually the Hamiltonian has to build up with just the Casimir operator of the total algebra. And
Yeah.
now you are
Adding it
with the sub
with the Casimir operator of
of the
subalgebra.
subalgebra.
Yeah.
But this actually can't be an Hamiltonian.
Yes, it can be. We will see. I will come
Okay,
to
okay,
a
okay.
very common example, which you know
Yeah, yeah.
from Pete's lectures. So, now let's get it a little bit more complicated, but important.
Sorry, so
Yeah.
could you go back?
Yeah.
Yes, so, one more, yeah. So, by you add the term B student prime,
Yeah.
it means you are considering more small situation.
Yes. So maybe I should before. Can I just jump a couple of transparencies to get you a concrete example, and then I come back to the more complicated things of irreducible. So let's go just forward a moment in order to make it concrete. Angular momentum, that's you know. So the Hamiltonian, we have the Hamiltonian, which the Schrödinger equation, time independent. And then we have this Lie algebra of angular momentum, so we have L plus, L minus, Lz, or Lx, Ly, Lz. Now the Casimir operator, we saw of O3 is L squared. Yeah? L squared commutes and always is equal to 0. Now if we have a Hamiltonian, the first of the supergroup, the higher group, we can say the Hamiltonian is A times L squared, and we know that the energies are then L plus 1 as a function of L. Yeah? And now what we do by having the subgroup, now the subgroup is O2, which is a subgroup of O3, and the Casimir operator we saw is Lz. Yeah? So now I make a Hamiltonian of the Casimir operator of the higher group, O3, and the Casimir operator of the lower group. Now, if you take L squared and A L squared and B Lz, then the solution is A L plus 1 plus B M. Yeah? And what you do by introducing this term, you just have, for instance, a magnetic field, and so the M degeneracy, which you had in the original symmetry, so we had 2L plus 1 different values of M here degenerate. Now, by applying a magnetic field, this degeneracy is split off, and so we get here the separate magnetic substates, but we do not break the quantum number L. That's the important part. L is conserved. Although now states are not anymore degeneracy, we still can classify the states by L and M, because SO3 has SO2 as a subalgebra or subgroup. Okay, let's return to some more complicated things, which you in some sense also know, but never have seen it in this kind of mathematical description. Irreducible representations. They are extremely important because they make it possible to actually do calculations. Without this property, it would not be possible to do calculations because the matrices would be so gigantic that you cannot diagonalize them. Now, since for every generator there is this matrix AK, which describes these transformations, they form a matrix representation of the algebra. Let me just return to give you what we mean by these matrices. Yeah. So if GK is working on a state gamma and small gamma, then it can only produce other small gammas, but it cannot change the big gamma. So that's the matrix representation. Now, if we have these matrices, we can apply unitary transformations on them. And the important thing is that we can make a block structure of a big matrix in which we have many zeros. These are zero blocks, so this can be 4 by 4 or bigger and so on. And then we have certain parts which we cannot transform in a block structure anymore. If we take the example of angular momentum, this was also discussed yesterday by Mark, we have this kind of cross product of a j value and a j prime value. Then it turns out that we can transform this in such a way that we have now values of j minus j prime, j minus j prime plus 1, up to j plus j prime. This is the vector coupling. Yeah? Vector coupling. And we cannot transform away inside these blocks. Now, but on the other hand, all the rest of these matrices are zeros. And these values, j minus j2 up to j plus j2, form what is called an irreducible representation. Now, what is important here is that there are rules. These are these Clebsch-Gordon coefficients mentioned yesterday, or 3j symbols. If I have j and j prime as irreducible representations of SO3, then I have rules how to couple them to form new irreducible representations of SO3. And these new irreducible representations are just these combinations. If I have 2 and 2, I can go to j0 and up to 4. Yeah? So important is these are irreducible representations and these are irreducible representations. Again, trust mathematics, they have done everything. I have rules how to define all these irreducible representations. To explain that would take a semester course, and I cannot do that. Now, you know these transformation coefficients as the Clebsch-Gordon coefficients from your basic quantum mechanics. I hope it's still given, Clebsch-Gordon, because solid-state physicists don't like that so much. Now, there are rules, I said there are rules to define how to combine irreducible representations. They have been invented by mathematicians and physicists, Wigner and other. So if you have now these quantum numbers, which I called alpha, beta, gamma, they label the irreducible representations, and generally this is done by a partition. So a general group can be characterized by a set of L integer numbers called a partition, such that the first one is higher than the second one and the third one and finally up to L. And the sum is equal to the number of particles. This can be fermions, this can be bosons. So L is called the rank of the group, and you can pictorially present them by a Young tableau. So for instance, if I have 10, 6 and 0, then I have 10 boxes here and I have 6 boxes here. Interesting is that this representation has some properties. If you have bosons, then you can only have one row, identical bosons, because these are symmetrized, and following the generalized Pauli principle, for bosons you need a symmetrized wave function, while the columns, like here, are anti-symmetrized. So it means if you have 5 half fermions, then if you have 4 of them, you cannot have 2 fermions with the same symmetrized quantum number, so they have to be anti-symmetrized. So it means you can only have one box here, one box here, one box here, one box here. And now I would like to mention something very important that you have to realize. If I have 5 half fermions, I have 6 substates. If I have S and D bosons, I have 6 substates. Both are described by a unitary transformation in 6 dimensions. Yeah? So it's not so that SU6 is associated with S and D bosons. No, SU6 can be realized using fermionic generators and can be associated with J 5-half fermions as well. So there are different realizations of the groups. Now, here I list the order and the ranks of the different groups in order to be complete. Now, as I said, mathematicians have solved all the mathematical problems, and so here you have the description of, for any group UN, how the Casimir operators are constructed is not given here, but the eigenvalues of the Casimir operators are given here as a function of how many quantum numbers you need to label, which depends on the rank of the group. And so you have general prescriptions for all groups that are available. Now, I come to the important thing we started with. What is the dynamical symmetry? First of all, what is dynamics? Dynamics is described by the Hamiltonian. Yeah? The dynamics of a system, quantum mechanical system, is described by the Hamiltonian. Symmetries, we have seen, is associated with Lie algebras and has to do with this commuting set of generators, which form then the Lie algebra G. Now, Hamiltonians are made out of operators. Generators are operators of the Lie algebra. So, if we now combine both, so we know that we have to construct a Hamiltonian out of the generators of operators, and if we now take these operators to be the generators of a Lie algebra, then we know that there exist special generators like Casimir operators, which commute without generators. And now, if we have a dynamical symmetry, we will now combine the dynamics of a quantum mechanical system with the symmetries by constructing a Hamiltonian out of generators, especially out of Casimir operators, which are constructed out of generators of a certain Lie algebra. And if we do that, then we saw before that we can now construct degenerate wave functions by just applying on a known wave function with a certain value of the energy, these generators on this known wave function, constructing new wave functions, and they all have the same energy. They are degenerate. And if we now can construct a chain of subalgebras or subgroups by considering from the original set of generators a subset and a subset of the subset and a subset of the subset of the subset, then we can construct a Hamiltonian which has coefficients, Casimir operators of these subalgebras, and then we have a solution which has now quantum numbers and which has an analytic expression for the energies of these Casimir operators of the subgroups. So this is what I showed before in the case of angular momentum, where it's natural to you to do that. Now, the last important point is the Wigner-Eckert theorem, which we discussed also partially yesterday. Now, often you have to calculate matrix elements between different wave functions. So wave functions, let's take just O3 and O2. They are classified by angular momentum J and the projection M. Now, if this operator also, and that's important, also has a good angular momentum, small j, and a good projection, small m, then one can apply the Wigner-Eckert theorem. And what is the Wigner-Eckert theorem telling you? There is a kind of 4 factor here, which is a geometrical factor, which has to do with how the values of m are contained in the values of j, and there is a matrix element which is independent of this. It's called a reduced matrix element, and it only depends on the quantum number of the higher group, j, small g, and j prime. These values, again, are tabulated by physicists and mathematical physicists and so on. And so they hold for every combination of those. So it means that if I have here a 5 state, L equal 5 and an L equal 4, then I have here 9 and here I have 11. So I have 99 matrix elements. It turns out there's only one which is essential, the reduced one. These are tabulated coefficients. So instead of having to calculate 99, I forgot, no. I also have here different values of m. So let's say that j is 1, then I have 99 times 3 elements, which I should calculate. Here, only have to calculate 1. So it's an enormous reduction of what you have to do. Moreover, what I mentioned yesterday to Mark, most of these coefficients are 0. Because you have rules, these are irreducible representations of O3, these are irreducible representations of O2. And there are rules. You know that m has to be from minus j to plus j, and there is a change of 1 between every m value. On the other hand, you have rules in this direction, that the sum of the magnetic projections has to be equal to the final magnetic projection, so you have kind of multiplication rules on the O2 level, you have multiplication rules on the O3 level. You need a vector coupling, you cannot couple a 2 with a 1 to a 5, it doesn't work. So it means there are a lot of funny rules in these coefficients, making that most of them are 0. And again, 3 times 99 matrix elements reduced to 1. So that's why symmetries are so important. Yes?
At first you started working, the first way, when you were working with S bosons and P bosons, your basis was S and P bosons.
Yeah.
And if you want to calculate matrix elements in these bases, how good is this thing for calculate?
I will come to that. That's the next thing. This you know for quantum mechanics, advanced quantum mechanics, I hope.
Yeah.
You learned about the Wigner-Eckhart theorem. Yeah? Now, we want to go a little bit further. Because this holds for all subalgebras. Not only for SO3 and SO2, but concerning your question, it also holds for U6 to U5. Yeah? So, that's the generalized Wigner-Eckhart theorem. So if I have a group, general, and a subgroup, and I have this irreps classified by these quantum numbers gamma and gamma, then if I can define a tensorial operator, T, to have a certain tensorial character gamma and gamma under these two groups, then the following holds, and that's the generalized Wigner-Eckhart theorem. So I can write all these matrix elements as a function of a geometrical factor given by group theory and a reduced matrix element, like in the Wigner-Eckhart theorem. This factor is called an isoscalar factor, and this is a reduced matrix element. And again, important is that in these isoscalar factors, most of them are 0, because I have now also rules combining this irreducible representation with this one will only yield certain irreducible representation, and a kind of reduction rule, which irreducible representation of the lower group is contained in the irreducible representation of the higher group. So that's a very important thing So the Wigner-Eckhart theorem does not only hold for angular momentum, but it holds on a much higher level.
There is a question, yeah?
Yes?
Yeah, I was just wondering what exactly isoscalar meant in a generalized group theory context.
Isoscalar, you have also isospin, yeah? And there the term isoscalar is also used.
Right. So
Maybe Pete can answer
Yeah,
this.
I think there is no relation with isospin, no?
Yeah, no.
I don't-
Oh, it's a general.
I think the term would be rather generalized coupling coefficient. An isoscalar factor means you can factor it out
Yeah.
in different parts.
Now, if you have now a chain, yeah,
Yes.
of
okay.
subgroups, then you can first apply it to the higher group. So now you have here many quantum numbers, and then you do it first to the higher, and then you have this factor, and then you continue. Now you reduce the reduced matrix on it, and then you have 3 lines or 4 lines, and then of course for every subgroups there are separate factors. That's what you mean. Eh?
Yes.
So you can factorize it, yeah? And probably that's the reason why it's called isoscalar factor. But it's
I think the problem
generalized
is-
Clebsch-Gordon coefficient you can also, or 3J, or so you can continue with this. Okay, now we come to part 1 after this rather long introduction.
Jan, there is
Yeah.
a break at 10:30.
I know, I just watched
Okay.
my clock. So, the interacting boson model. We will discuss even nuclei. That means an even number of protons and an even number of neutrons. Yeah, it's 1/4 of all nuclei. And so generally, we have 8 nucleons. A can be 168 or something like that. And that's much too complicated to do in ab initio. Mark Caprio will talk about that on Thursday. You can go up to 12 nucleons or something like that, but not up to 150 or something. So that means that we have to do some truncations, and one of the important truncations is the existence of shell structures. So we can see that the protons and the neutrons, they form closed shell with large gaps. And so we can, instead of starting with all these fermions, which is a huge number of nucleons, we can now go over to valence nucleons. So it means if we have a closed shell, then everything couples to 0. Yeah? All the magnetic substates are present, filled, so it all couples to 0. And so we can consider the closed shell, especially of a double magic nucleus, as being inert. Yeah? So it doesn't contribute to the collective excitations at low energy. So this is a huge truncation of our model space. Instead of having 150, we now have to consider 20 nucleons, for instance. So that's the first reduction, but it's not sufficient in medium heavy and heavy nuclei. There are still too many of them. And so we now use another property. The property is that nucleons tend to have a stronger interaction if they move in opposite M states, magnetic states. The reason is they cannot move together in the same M state because they are fermions, Pauli principle. And so in order to come the closest as possible, they just make orbits with different M states. So one's in this direction, one's in this direction, then they will be close twice when they orbit around the inner core. So this is a pairing property, which will be discussed next week by Machiavelli. And so we can now consider that we only describe nucleon pairs. Now the question is, of course, if they are in opposite M values, they couple to 0. And the next possibility is that they couple to 2. And so we can now restrict ourselves, truncate again our model space to L equals 0 and L equals 2 pairs. And this is still a very difficult problem. because these are nucleon pairs made out of fermions. And so the proposition made by Iacello and Arima is a very drastic one. Let's just replace these fermion pairs with L equals 0 by an S boson, an L equals 0 boson, and this L equal 2 pairs by a D boson. So we do a boson mapping.
Excuse me.
Yeah.
Why there are only S and D?
Because we have identical nucleons, and because of the Pauli principle, if you you need to have an anti-symmetrized wave function. And this is a very amazing thing. If you construct now fermions with spin half integer, and you impose anti-symmetrized wave functions, it turns out you cannot make an L equal 1 state.
Yes.
Yeah.
So
If you do the same with bosons, bosons have integer spin, and they have to be symmetrized. It's exactly the same. They cannot make an L equal 1 state.
yes.
Yeah, I showed that in my first lecture also
Okay.
with the M scheme. I think his question was why not L equals 4?
Yes.
No. We will come in the exercise.
That's
We will
what I
introduce a
think
G
he meant.
boson. Yeah, you can introduce. The reason is that all even nuclei have a L equals 0 ground state, and all even nuclei except 4 have an L equal 2 first excited state, and then you get a 4 state. And so you truncate as much as possible by taking only S bosons would not make sense, because you will predict that only the ground states of even nuclei. And so you take the next, the D boson, which also has the advantage that it in some sense corresponds to a quadruple phonon. Yeah? So that's why you do that in first instance. And it will turn out, we will show it, that you get a very simple Hamiltonian. If you include more bosons, then your Hamiltonian becomes more and more complex, and it means the number of parameters increases. And that's also something we can have.
Yeah. Can I just make a quick comment? Remember when we looked at the delta function residual interaction?
Mm-hmm.
The lowest state for two identical fermions was 0, and the next one was 2,
And then
the others were higher. So this is an approximation
Yes.
to take those lowest energy couplings.
Historically, the story is different. Historically, the story started with quadruple phonons, U5, and then the S boson was introduced in order to allow to describe not only spherical nuclei but also rotational ones. But we will come to that. So this was done by Akito Arima, Franco Iacello, and then later more microscopically for the mapping by Takahura Otsuka and Igal Talmi in 1974 to 1979. Now, Schrödinger equation in second quantization, Fock, again, has showed that you can go from the Schrödinger equation to a new form, which is a kind of occupation number representation, which is called the second quantization, and consists of creation and annihilation operators. And you have the matrix elements of the Schrödinger equation, the kinetic energy and the potential energy here. And so this is the most general Hamiltonian in second quantization up to second order, up to two-body interactions. Now, if you work it out in detail, then you find that if you have an SND boson system where n is a constant, yeah, so a given nucleus, you make the interpretation, bosons are coupled valence nucleons, so then if I have a given nucleus, then I have a constant number of valence nucleons, so I have a constant number of bosons. Now, if you work it out, this general representation, it turns out you get a 6-parameter Hamiltonian. So 6 parameters, one here, epsilon nd, one for the angular momentum, L squared, and then Q squared, then coupled to 3 squared, and coupled to 4 squared, that's 1, 2, 3, 4, 5. And in the quadruple operator, which is the only operator where you can make a mixture of S and D bosons, S and D coupled to 2, or D and D coupled to 2, I have here the sixth parameter, which is denoted by phi. So that's amazing because you only have 6 parameters and you have the most general Hamiltonian of an SD boson system. Now, if we look a little bit more in detail, then we notice that the generators of these U6 groups, they are just the combinations of creation and annihilation operators of given values. This is a special value because of the angular momentum, so it's not an annihilation operator, but it's an annihilation operator with a phase factor and a change of n in order to conserve the angular momentum. So details, again, I cannot give here. Now, remember our funny idea about this 6-dimensional vector? So you can see here, I annihilate, for instance, a d-2 boson and I create an S boson or something like that. It's a bit more complicated because of angular momentum. We want this to have a good angular momentum and angular momentum projection. Now, if you work out the commutator of 2 of these generators, it is this beast. So it's a sum over other possibilities of kappa. You have square roots, you have Clebsch-Gordon coefficients, you have 6 J symbols, you have deltas, and so on. So, but they close. I mean, any commutator of 2 generators produces here one other generator linear and one other generator linear. Now, can we recognize certain parts of these subalgebras in this commutator? Yes, we can. First, you have to realize that if you have only d bosons, then of course if you create and annihilate d bosons, you cannot create or annihilate S bosons. So these generators have to close also among themselves. Now, what does this mean? It means that all the L values here are 2. And if you look now here, this 6J symbol, 2, 2, 2, and this 6J symbol, 2, 2, 2, are the same. The deltas are fulfilled, so I can bring out these, and both these, because they are also 2D. And so I obtain now a subset of generators, which are the generators only made out of d bosons, and they fulfill now a subset of commutation rules, so I can bring out this one with 2, 2, 2, I can bring out this one, because I cannot make anything else, and I have here a phase factor, which is -1 k, k prime, k double prime, -1. So we see that not only in the matrix we have a subalgebra, but also in the commutation rules we have a subalgebra by considering only d bosons. Now this more interesting is this phase factor, because if k and k prime are odd, their sum is even. And if k double prime is even, then I have here 1 minus 1, 0. So it means if I now consider only odd generators with L equal 1 and L equal 3, then I can only form these combinations without this factor multiplying with 0 if k double prime is odd. So it means that I have now a subalgebra by considering the 10 odd k generators, 3 with L equal 1 and 7 with L equal 3, and they form in fact this SO5 subgroup which we saw before. And then finally, if I only consider the ones with L equal 1, these are the angular momentum generators, so they form now a subgroup with SO3. And so the associated quantum numbers are n, the number of bosons, nd, the number of d bosons, tau, which is the seniority, and the angular momentum L. So this is the easy sub-algebra of the interacting boson model. There are 2 more, which I have no time to define them. The one is going immediately from the unitary transformations to the orthogonal transformations in 6 dimensions. So it's a reduction from U6 to SO6. It turns out you again can have this SO5 and SO3 subgroup for this chain. And finally, there is a chain going from U6 to SU3 and then immediately to SO3 to the L and then the M value. Interesting is that this chain, remember quadrupole phonons are equivalent more or less as the D bosons, they represent vibrational nuclei. This chain is what we discussed yesterday, this gamma unstable nuclei, so where the potential energy is flat in the gamma direction, and the last is the rotational nuclei. And in the original work, especially prolate rotors are represented by SU3. So historically, as I said, one started from this description of quadrupole phonons, and then one realized that if one added an S boson to it, you get this group, and then one realized, one introduced this S boson in order, because one knew that then rotational nuclei could be described as a subgroup. SU3 is not a subgroup of U5. The bonus was that one realized that there is a third chain, which was not built in, but it was discovered afterwards, which is this SO6 chain, with which Rick has a lot to do. Because it turned out that actually nuclei existed, which are very well described by this Hamiltonian. As an example, 110 Ca is a vibrational nucleus, can be described by U5 symmetry. 156 gadolinium has a rotational with a rotational iris band, a beta and a gamma band, and can be described by this SU3 symmetry of the interacting boson model. And as a bonus, SO6 symmetry was predicted, and it turned out that platinum 196 is quite well described by this gamma unstable limit of the interacting boson model. Again, using our algebraic approach, we can now add all Casimir operators of these different groups up to second order Casimir operators. And again, it turned out we have 6 of these Casimir operators, and we have 6 parameters, like we had in the most general solution. So this is something we will study, for instance, in the afternoon numerically. Now, I would like to warn you, if you mix groups of different chains, like U5, SO6 or SU3, the parameters, the quantum numbers are lost. The analytic expressions are lost. The wave functions depend on the parameters. So if you take this general Hamiltonian, it's an error many students make, and you plug in here the analytic values of these Casimir operators, you're wrong. It doesn't hold. Analytic solutions are possible if you take a dynamical symmetry. It means one of these subchains of subgroups. For instance, the U5 limit, you take Casimir first order of U5, second order of U5, then of SO5 and SO3. You plug in the eigenvalues and you have an analytic solution of your many-body problem. The same holds for SU3. You see here the description is more difficult because in U5 you have 5 parameters, and in SU3 you have only 2 parameters. Here, these 2. And this is the analytic expression. In SO6 you have 3 parameters because you have only quadratic Casimir operators, and this is the analytic expression. And there are also analytic expressions to relate the L values contained in the lambda mu values, and the lambda mu values contained in n, the number of U6. But I don't want to give this reduction rules here.
So,
yep.
Yeah, so you said that we cannot take all these groups and take their...
Just S decker T plus D decker S. Now this has consequences, because that means that it's an SO6 scalar, so it cannot act outside the SO6 representation. And we can write down the tensorial character of this operator. It's, of course, 0. Then it's 0, that's the SO6 scalar property. Then, of course, it's 1 for SO5, and it's quadruple operator. Now, the consequence of this is that if E2 transitions between different SO6 representations are absolutely forbidden as long as we have a good SO6 dynamic procedure. Now, this is platinum 195, and what is given here on top are the SO6 quantum numbers. So these states all have SO6 quantum number 6. These have SO6 quantum number 4, and these have SO6 quantum number 2. So it means that if the SO6 symmetry is a good one, E2 transitions from this 2 plus state to the ground state are absolutely forbidden, or to any of the other states are absolutely forbidden. So that's a clear prediction, yes?
What is the maybe physical or intuitive picture of what the SO6 quantum number represents?
Not so easy. For SO5 you have this seniority concept. For SO6 you don't really have such a concept, except maybe it
No,
knows.
it's also seniority, yeah? But then it's a combined
Of
SS and
SAT.
these.
Yeah. So it's kind of generalized seniority. Now, maybe just to mention, the lowest states have the maximal quantum number for SO6, which is called sigma max often, and it's equal to the number of bosons. So then the next, I have the number of bosons minus 2, and then so on. That's the reduction rules from U6 to SO6. Now, the Rick, in fact, and Jolie have used additional selection rules on the O5 level in order to identify platinum 196 as a good O6 quantum. So you use here now this O6 tensorial character in order to associate the states to these different quantum numbers. But there has not been a test for many years of this E2 selection rule between states having the different sigma quantum numbers. Recently, the group of Norbert Pintarella and my group have now completed a test and come to the same result, which unfortunately I have not included in this talk. But about many years ago, 14 years ago, I took 24 years ago. Man,
You were young
old.
then. You were young then.
Yeah, I was young. Together with Rick.
I was old.
Yeah, he was already old. We did an experiment using a special technique, which is called the gamma ray induced Doppler voting method, and we determined the lifetime of these states, or we could not really determine the lifetime, we determined an upper limit of the lifetime of these states. And now you have to see that these states, they belong to the higher or the lower O6 quantum number, and so the transitions to all these states are absolutely forbidden. And only the transition E2 from this state to this state is allowed. And so we have here also a theoretical prediction that this is allowed, or from the fifth 2 plus to the fourth is allowed. And other ones are all strictly forbidden. And so we could determine experimentally that we have an upper limit which is very small for all these states, and recently we determined a lower limit. And so we could show that, okay, they are not exactly 0, but they are almost compatible with 0. So it means that we could test these quantum numbers to be trustable in that way. There is another selection rule concerning O5, and there it turns out that this selection rule causes a problem because it says that all quadrupole moments should be equal to 0 because of this O5 selection rule, which says the value of the O5 quantum number should change with 1. And of course, if you have the same state, then the value is not changing. And so, because of the O5, all quadrupole moments are forbidden. And this is experimentally not really the case, because experimentally we will come to that a little bit later. The quadrupole moment is non-zero, but it's still small for a quadrupole moment. Okay. Now I come to the next subject, which is partial dynamical symmetries. Now, dynamical symmetries, as we saw them, they lead to solvability of the complete spectrum. Existence of exact quantum number for the complete spectrum. And predetermined structure of the wave functions independent of the used parameters. That's what the dynamical symmetry poses. Of course, nature is not always very generous, and nature does not always fulfill these three conditions of a dynamical symmetry. And so we can now relax on these conditions and construct Hamiltonians such that only some states keep all the quantum numbers, that all eigenstates keep some of the quantum numbers is another possibility, and finally, if we combine both, that some eigenstates keep some of the quantum numbers. Systems exhibiting one of these three conditions have a called partial dynamical symmetry. And so we will see that with the example of some concrete examples. First case. Consider that I mix the U5 dynamical symmetry. U5 is U5 plus SO5 plus SO3. And the SO6 dynamical symmetry, SO6 plus SO6, SO5, and SO3. So if we mix now, I have here a kind of tuning parameter alpha, which I can switch on and then switch off the U5 term and switch on the SO6 term. Generally, these have not a dynamical symmetry, and the complete spectrum cannot be solved analytically. However, because both groups have SO5 as a subgroup, followed by SO3, the quantum numbers, tau and L and M, are conserved all over this transition. The analytic expressions are not conserved, but the quantum numbers are conserved. So it's a symmetry in which all eigenstates keep some quantum numbers. As an example, here you see the spectrum. Alpha being 0, you have the U5 spectrum, and here the two phonon states, 0 to 4. And if you now switch on alpha and alpha becomes 1, you have the SO6 spectrum, where you have a different sequence of states. And especially this 0 plus of the two phonon, which was discussed, it's going up, and it forms the lowest state of this other sigma max means 2 O6 quantum number. However, in the whole transition, the seniority of this state is 1, and it stays 1 over the whole transition, becomes seniority 1. This is seniority 2, coming from here, seniority 2, and the seniority quantum number is all over the transition. So, next week there will be the 15 Capture Gamma Ray conference, and so this is the cover of the 1993 Capture Gamma conference. And what you see here is the wave functions plotted in a U5 basis for the states. You see this kind of peaked structure, and many elements are 0, yeah? Overlap. And this is a consequence of this conservation of the seniority continuum. So you can see that more clearly if you now compare it, if you do this expansion in an SU3 basis, so any basis can be used to make a numerical calculation. You have this many small components, but if you are in between, then you get this conservation of the O5 quantum numbers. Now an example of case 1 we will construct is partial dynamical symmetry within the SO6 limit. So this is again platinum, 196. These are the sigma max states with n equals 6, then sigma equals 4, and then sigma equals 2, which we discussed before. And this is the theoretical spectrum. If you look for the sigma max state, the description is rather good, but here there are some deviations in these higher states. So the question is, can we now construct a Hamiltonian which keeps the symmetry for these states, but changes the energies and wave functions, or mixes them for the higher line states in order to get the description?
So before
Yeah.
you go to the next slide, I was wondering if the angular momentum of these states can be measured.
Yeah.
Can the sigma be measured, or is this something we just prescribe by the model?
We can measure it by using the selection rules, more or less. And also, maybe I didn't mention that, we have analytic expressions, we have analytic wave functions, yeah? And then we have the operator, and so we can now calculate transition BA2 values as a function of the quantum number. And so these formulas we can now test. So, and in this sense, we can test other quantum numbers, like we test angular momentum.
It's not directly measured,
No,
but it's deduced.
yes, yeah. Deduced, yeah. Now, how can we do that? The first step is we need to construct operators which have a definite tensorial character under the SO6 limit. And so I have here the example. How can we do that? We just calculate analytically the wave functions in the SO6 limit for two S and D bosons. Yeah? So n is 2, and then I can have sigma equal to 2 or 0. And then I can have seniority equal to 2, 1, or 0, and the L value is equal to 4, 2, 2, 0, 0. Now, this is just using the analytic expressions for the symmetries. And then, of course, we have the wave functions also analytically, and these are these combinations. Yeah? This is, again, this vector product. This is 2, 2 coupled to 4, 2, 2 coupled to 2, and so on. Now, the interesting guy is the last one, because this guy has n equal 2, but it has sigma equals 0, while seniority equals 0, and L equals 0. So it's a scalar under O6, O5, and O3. The expression is given here. It's minus a term square root s decker coupled to 0, and then plus square root 5 divided by 12 d decker coupled to 0. Now, this we can use now to construct a partial dynamical symmetry. How? We choose an interaction such that the interaction working on states with a given sigma always yields 0. And this interaction, we use this two-particle wave function with sigma equals 0. Yeah? So that's, again, this operator, this expression. And then the other one is the same with annihilation operators. So this interaction has then this tensorial character. Yeah? And if you work it out, you can write it in terms of this, what is called a boson pairing operator. Now the important thing is, if I work on a state with maximal value of O6 quantum number, so n bosons, and it's n, sigma is equal to n, then I end up with the annihilation operator in a nucleus with n minus 2 bosons. And then the maximal value of sigma is n minus 2. And there is no state with a value n by this annihilation. And this is now a scalar operator. So the irreducible representation null times n can only yield in the vector coupling at an abstract level n. But n is not present. So it means that if I work with this interaction on this maximal O6 quantum states, it will always yield 0. So it has no effect. However, if I use now this interaction and I work on a state with lower sigma quantum numbers, like n minus 2, null times n minus 2 is n minus 2, but I will end up in an atomic nucleus with n minus 2 bosons by this annihilation. There, these states are present. So it means that this interaction will only act on states having not the maximal value of the SO6 quantum.
So, what does this top line mean then again?
We choose an interaction which is such that for certain states, the interaction yields 0. Now, I do it here explicitly only with the annihilation, yeah? But of course I have to return in the same nucleus. Yeah? And that's why I need to have a creation and an annihilation operator. But the annihilation already yields 0 for this sigma max space. So if I then multiply it with the creation, 0 times something is 0. Okay. Now, so this is the way one can construct partial diameter symmetries, and in fact we will do it in the lesson 3 minutes in the afternoon. We will also construct a partial diameter symmetry and program it yourself. So if we have the Hamiltonian SO6, SO5, and SO3, that's a normal O6 Hamiltonian, I can now add this interaction here, P plus P minus, with a parameter. If I have the parameter equal to 0, I get just the original O6 spectrum, which I can compare with platinum. And if I now vary the parameter, you see all these sigma max states, they don't change anything, their energy is not changing. On the other hand, these states are changing their energies because these are coming closer compared to here and closer to experiment, and also here they are coming closer. So that's an improvement of this O6 by using the concept of a partial dynamical symmetry. I want to conclude with some practical things. How to determine the tensorial character of an operator. Yeah? In order to find out selection rules, one needs to have this good definition of the tensorial character of the operator, because otherwise I cannot use this extended Wiener-Eckart theorem. Now, there are some tricks how to do it. Let's take a transfer operator. Yeah? So we go from one nucleus in another even nucleus by a transfer reaction, for instance, PT transfer, and that of course corresponds in the model by creating an S or a D boson state. Yeah? So two particle transfer reaction. And now how to determine the transfer operator's properties? It's very easy. You just take the reduction rules in the O6 chain, and I give them here, so sigma is the number of bosons, minus 2 and so on. Tau is given as a function of sigma, and L is given as a function of tau here. With a missing label, it's a bit more complicated. But you have these reduction rules in textbooks, and so you now have a very easy task. You just take one boson, so then sigma is equal to 1, tau is equal to 1 and 0, and L is then corresponding equal to 2 for the D boson and 0 for the S boson. So we have here the tensorial character of these transfer operators in the simplest form, immediately derived by using the expressions for the wave functions or the reduction wave. Second example, which we discussed before, is again the example with this partial dynamic asymmetry. We just look at the wave functions for two boson system, and then we select those which have in sigma 0, 0, 0, and then this is the expression of the wave function from the textbook. And so we can now have this operator by just taking this combination, and we can rewrite it as a scalar product and things like that. So this is the same trick. In fact, we just put in small values of the bosons and do the reduction. So with this, I would like to end my first lecture. Yeah.
Sorry?
Yeah.
You define the P plus, but what is P minus?
P minus is the annihilation operators. So I use this table because this is as a function of the creation operators, but you just change the creation in the annihilation, and then you have the P minus. Because you have to end up in the same nucleus again. So if I remove two bosons, then I have to add again two bosons. But in the removal of the two bosons, already this partial dynamic asymmetry takes place. Okay, now this was the end of lecture 1. So now I have to just change to lecture 2. That's not so easy. The lectures will be available on the website. I hope this will be clear. Now I will come to another subject which is associated with the shape of a nucleus. Yeah? So we will discuss now shape phases and critical point solutions, which will be discussed also in detail tomorrow by Norbert Pietrala. Now, most nuclei are very well described by an extremely simple IBM Hamiltonian due to this guy. My fault. It's your fault, yeah. Now, it's called the consistent Q formalism, and it has two terms. It has a Casimir operator ND. It's the first order Casimir operator of U5, and the quadrupole operator as a function of this parameter chi. Remember, this was the sixth parameter we had as a scalar product with itself. We have.
Jan, I have to interrupt. Yeah. You got to give Dave Warner credit.
And Dave Warner. Yeah. You have a structural parameters eta here, which is again of the type that I switch off the ND term and switch on the QQ term by varying eta. I need some normalization by the number of bosons because this is a quadratic term and this is a linear term. And I have a scaling factor, so I can expand. The structure of the spectrum is given by eta and chi, and this is just an adaptation, the scaling factor expanding the spectrum in order to compare with actual nuclei. So two structural parameters, eta and chi, and a scaling factor. Now the first term generates spherical shapes. Yeah? These are quadrupole phonal vibrational nuclei. While the second term generates deformed shapes. This is a part of the Casimir operator of SU3, and it makes deformed structures. And so we have a kind of Ising Hamiltonian in which we have two competing structures which we can, by a control parameter, switch on and switch off. Now, remember this custom triangle? We have now eta in this direction, in fact going eta 1 is u5 here, and chi going like this angle in this direction. Now, the amazing thing is this is a very simple Hamiltonian, but it has 4 dynamical symmetries. So the first one is eta equal 1, then I have the u5 limit of the interacting boson model, and this is situated here in this corner, where eta equal 1 and chi has no influence. Then the second dynamical symmetry it has is if we take eta equals 0 and chi equals 0, then I am in the SO6 limit of the interacting boson model. So we define this point here, and so here chi equals 0, we have a SO6 dynamical symmetry. Now if we take eta equals 0 and chi with a special value minus square root 7 divided by 2, then I'm in the SU3 limit. So I have the deformed nucleus, prolate deformed nucleus. So this is situated here. And then finally, if eta is equal to 0 and chi is plus 7.5, I have this SU3 bar symmetry. So these are defining oblate rotors. And so we see here, with these 2 parameters, we have 1, 2, 3, 4 dynamical symmetries. The interesting thing is that we can now study how you go over from one of these dynamical symmetry-like nucleus to another one. For that we use now the formalism of the coherent state formalism. So again, this is the energy for n bosons with the parameter eta and chi for different values of beta gamma. And I have this expression. It has a beta square term, it has a beta to the 3rd cosinus 3 gamma term. Remember that was also something Mark had, and then a beta to the 4th term. Now this term is interesting because beta I 3 cosinus 3 gamma, beta is always a positive value, and so if chi is negative, then cosinus 3 gamma has the minimum at 0 degrees. So these are the prolate shapes. However, if chi is positive, then this term is positive, and then we need to have here minus 1. And so the minimum is then at 60 degrees. Yeah? So this term is defining whether we have a prolate or an oblate shape. Now, shape change in atomic nuclei, it's a little bit complicated compared to solid state physics. Now, how can we observe shape phase transitions in atomic nucleus? We can look at the deformation of the ground state. If we have a spherical nucleus, then we have a spherical deformation or no deformation of the ground state. However, if we have a rotational nucleus, then we will have a prolate or an oblate form for the spheroid for the deformation of the nucleus. Now, we can compare now that to phase transitions in crystals, in this sense, that if you have a phase transition in a crystal, you change some external parameters, and then you go over from one particular crystal structure to another one. And this happens, in general, as a function in solid state physics, as a function of pressure, temperature, or concentration of certain impurities and things like that. Now, in atomic nuclei, this happens as a function of the number of valence neutrons. So if you have a low number of valence neutrons, you generally have a spherical nucleus. If you increase the number of valence neutrons, then you will get a transition to a deformed nucleus. Now, for solid state, this guy, Landau, Lev Landau, you know probably from Landau and Lifshitz, physics books, described this kind of phase transitions in 1937 in a general way. And he started from a thermodynamical potential, thermodynamical potential phi, which also has external parameters like the pressure and the temperature you can vary, and which has an order parameter, psi, which describes the structure. For instance, the crystallographic structure. Now, in order to do that, we have extended this Landau to atomic nuclei, and so instead of having a thermodynamical potential, we have an energy functional, which is given by this coherent state formalism. And so we have now the energy as a function of the number of bosons, eta and chi, and we have two order parameters because we have the description of the deformation is done by these beta and gamma variables, which Mark Caprio introduced already yesterday. So we see there is some equivalence between both, but instead of one order parameter, we have two order parameters, and instead of two external parameters, in principle, we have three with the number of bosons. Now, how does it work with Landau? So consider we have here the temperature axis and the pressure axis. So now what you have to do is you have to minimize this thermodynamical potential as a function of a given P and T. So at this point we have P1 and T1 given, and then we minimize and look for the minimal value for the corresponding order parameter. So you have to imagine in every point, this is with a constant pressure, you have this kind of energy functional or thermodynamical potential, and you look now for the psi value. This is the psi axis, which corresponds to the minimum. And this, of course, will vary as a function of, in this case, different temperature, constant pressure. Now, if you do that, you can observe phase transitions. And how do they come along? So you have different orders of phase transition. The first order phase transition, let's take the case that we vary by constant pressure, we vary the temperature. Now, what you will obtain is that the thermodynamic function at the beginning will have, for instance, this minimum here at psi equals 0. But then if you now decrease the temperature, then there might be a second minimum developing, but being higher in energy, and at a finite value of psi not equal to 0. And then at the critical point, or the critical temperature, both minima become degenerate. So they are at the same energy, and if I now lower the temperature further, then suddenly this psi becomes the only minimum further. So this is our order parameter, psi. Now if you plot what is happening as a function of temperature, then you have for high temperatures, sorry, the axis is wrong. It should be inverted. Let's assume that this is a higher temperature and this is a lower one. Then, as long as you have this minimum, then you have a certain value for psi, and then if you pass the critical temperature, then suddenly you will have the change of the energy of the minimum. And if you now look at your order parameter, which defines where the minimum is, or psi minimum, then you see a sudden jump in the order parameter by a first order phase transition. So it was 0 the whole time. At the critical temperature, it suddenly takes a finite value, and then it increases as the minimum moves in that direction. Now, you can have another case, which is the second order phase transition, in which the potential smoothly rolls from the 0 minimum into a higher minimum. Yeah? So there is no really second minimum, but it smoothly moves, so it's the whole time 0, and then suddenly it changes value. And if you look at the minimum value, then also it is 0, and there is a kink here, and this increases then as the minimum is getting more to higher values. So that's a second order phase transition. Now, what does Landau do in his theory? He assumes the form of the potential as a function of pt and psi to be a constant value, and then a term with psi squared, psi to the third, and psi to the fourth power, and then of course here you have functions which depend on p and t. Remember what we had before? We had as a function of beta squared, beta to the third, cosinus 3 gamma, and beta to the fourth, these energy functional, and in front were coefficients depending on n, eta, and chi. So it's very simple. Now, Landau considers the case, among other cases, in which beta p, this term, with the cubic term, is non-zero for everywhere. And of course, this term has to be negative, otherwise this will always yield a minimum at plus infinity. So we have to say pt should be bigger than 0, and beta is non-zero. Now, in the case as a function of p and t, we can define now that the function thermodynamic potential should be continuous as a function of p and t everywhere. But if derivative can be discontinuous at a certain value, and if we have, then we have a first order phase transition. And if the second derivative is continuous at a certain value, but not the first one, we have a second order phase transition. This is the Ehrenfeld classification of phase transition. Now, if we first look for the extremum, so where the minimum has to be, by taking the derivative of psi of this function, and if you do that, you get this equation, psi multiplying by 2a, 3b, psi 4c, psi squared is equal to 0. And so we see already two possible solutions. Psi is equal to 0 is a solution, or the second term is equal to 0. And then it depends, of course, which one is yielding the lower value of the potential, yeah, in order to find the real minimum. Now, in our case, P is not equal to 0, C is bigger than 0 for all P and T, and so we can now work it out. So we have the minimum either at psi equals 0 or at psi equal to this solution of this quadratic equation. Now, first we consider the case that psi is equal to 0. In that case, we need, of course, that A to be a positive term. Otherwise, it would be a maximum and not a minimum. The parabola can be like that, or it can be like that. So we find the condition for the minimum psi equal to 0. We have positive values of APT. It might be that some of these values are excluded because we get another minimum, which is lower. This is a necessary condition, but still there may be, that's exactly what I've written down, there may be a deeper minimum at another value of psi. Now, let's go back to our potential. We saw that the phase transitions will happen, for instance, for the first order, when we have two degenerate minima. One at psi equals 0, and one at psi non-equals 0. But if psi is equal 0, if we look at this expression, all these terms yield 0, and so we get the minimum is phi 0. Let's take phi 0 equal to 0 to make it easy. So then we get the potential is equal to 0. Yeah? And now we can impose this condition. So phi, the first term is 0. And then we can put psi squared outside, and we again obtain a quadratic equation, however with different coefficients here, which we can solve. So if the second term becomes equal to 0, then the condition is it happens when b squared is equal to 4ac. Yeah? If this, then the square root in the solution becomes 0, and so I have a real number. So in order to fulfill this condition, we have now b squared is equal to 4ac. Now, if we insert this in our expression for, say, 0, this is the expression we derived before. Now we insert AC is equal to b squared divided by 4. If we insert that inside here, then it turns out there is standing here 8. Yeah? 32 divided by 4 is 8. And so I have 9b squared minus 8b squared is 1b squared. I can take the square root. And so I have now minus 3b plus or minus b divided by 8c. And it turns out that it's a minus sign, which yields the minimum. I'm sorry.
That happened once before. Use the arrows in your computer.
Yeah, but
It doesn't want you to do.
they don't work.
If
Is
you
it
go-
the battery?
Now there it goes.
Okay. Yeah. So we have this second minimum happens now at this critical value of the order parameter, which is equal to minus b divided by 2c. So if psi is bigger than 0, then b has to be smaller than 0 because of this minus sign. Remember, this is always positive. And if psi is smaller than 0, then b has to be bigger than 0. And of course, the condition was on a certain value for the a parameter given by this expression that the discriminant becomes equal to 0. And so this condition is given here again. And so we get a total picture of phase transitions. I mean, made by Landau, more or less. So here's a function of the parameters b and a. So b is in this direction and a is in this direction. We have these three different phases. The one yielding psi equals 0, which is given by this strict line that alpha has to be positive. Alpha is going in this direction. So this is the alpha 0 line. But you see here, this is the real phase transition. This is where the second minimum appears and disappears. So we go also slightly in the positive for phase 2 and 3, which correspond to positive and negative values of beta. And so the phase transitions happen at these lines and this line. So we will look a little bit more in detail to that. So if you look at the values of psi, so vertical axis is psi, that is parameter minus a, parameter b. Here, everywhere, the minimum is psi equals 0, psi equals 0, for the positive values of a. And then suddenly, we will have here a jump in the second minimum, which makes here the positive, the negative values of beta, and here the positive values of beta. And also here there's a jump to the first order phase transition here in this domain, and in this domain, and in this domain. And then in the center, where the three phases come together, you have a second order phase transition. Where it goes smooth. So second order, it looks like that. Psi is 0, and then suddenly there's no jump, but then it increases. The square root kind of behavior. So how can we now apply the same to our energy functional? Now, first of all, we have to realize that we have two variables, beta and gamma. Landau had only one variable. But we can now apply a trick. So, again, this gamma value is yielding for a negative value of chi, a minimum at 0 degrees, and for a positive value of chi, a minimum at 60 degrees. Now, we have to realize that if we have this expansion here, if you do the expansion, you only get quadratic terms. Yeah? Power 2, power 4, power 6, and so on. So, the B3 cosinus 3 gamma is the only odd value of beta in this energy function here. And that determines, as I said, with the sign of gamma, the minimum. So we can now use the trick. We absorb this cosinus 3 gamma in beta. Beta normally was a length, was only allowed to have positive values. But if the minimum is yielding the negative sign, then we just absorb it and we say beta is now allowed to have positive values for prolate rotors and negative values for oblate rotors. Then we have more or less absorbed one of the control parameters in the sign of beta. And of course we can now vary n, but we can also fix n. And most calculations are done using different values of n and varying the other parameters. So like that, is that are the patterns?
No.
Okay. So if we use this trick, then we obtain exactly the form at least at lowest order of Landau. No, it's not a battery.
No, it's not a battery.
No. So, and then we can fix n, and then we have exactly the form to lowest order of Landau. And so we can apply now Landau's theory, and as a result, and now our functions of B, A, and C are just a function of the parameters, the control parameters eta, chi, and n, given here. And so the first order phase transition is when A parameter is 0, so we can solve this and we obtain then this expression. For the spherical to deformed phase transition, and for the prolate to oblate, B has to be equal 0, and if B has to be equal 0, we obtain that chi has to be equal 0. Because chi it appears here in B. Yeah? So the isolated second order phase transition at crossing of the two lines is then A equal B equals 0, and so you can work it out and you get this analytic expression for the critical value of A.
Excuse me?
Yeah.
So we are now considering only axial symmetric case?
Yeah, no triaxial. It has been done for triaxial also, but it's much more complicated. In fact, Mark Capillo did it. But then you have the neutron proton debate. Okay, and so now we can apply Landau's theory to nuclei. So Landau's theory, we have three phases, one with 0 for the control order parameter, one with negative and one with positive. And we have exactly the same. Here the deformation beta is equal to 0, and here beta takes a positive value, including prolate rotor, and beta takes a negative value by this absorption trick, including oblate rotor. So we see that the Hamiltonian has 1, 2, 3, 4 dynamic asymmetries, and it has 3 different phases: spherical, prolate deformed, oblate deformed, and between we have first order phase transitions, and we have at this crossing point a second order phase transition at what is called the triple point of nuclear deformation, because you have spherical, prolate, and oblate coming together there. I realized this was again work with Rick. Okay. Now, how can we? How can we see that? We can see that in numerical calculations. What I plot here is as a function of chi and eta. So you have to see it. This is the triangle, but I plot the energy of the ground state in absolute value. And so you see in U5 actually is 0. We will calculate that also this afternoon. And then it becomes, if you go into the other phases, it becomes negative. And you see, at least you can imagine, this is a calculation for 40 bosons. If you look at from the side, you can imagine that if you go to an infinite number of bosons, the phase transitions become absolutely short. Yeah. We have quantum mechanical effects due to the finite number of bosons leading to quantum fluctuations, which makes that these phase transitions are not absolutely short. Yeah. Yes?
Excuse me, in the case of water, the point where the three phases coexist can be achieved, whereas in nuclear matter, does this point can be reached, and if yes, what
there are some candidates. We will see that tomorrow. There is something equivalent in the collective model, and these are called critical point nuclei. And the corresponding point of this point here has a symmetry which is called E5. Unfortunately, as far maybe Rick will say that it's not true, there are not really good candidates of atomic nuclei for an E5 symmetry. I think you proposed barium.
Well, we looked at barium-134 to see if it worked, and it sort of. So I would agree with your statement.
Yes, okay. On the other hand, here, for the spherical to deform, there is also a collective symmetry called X5, and there are several nuclei which are candidates, but I'm pretty sure that in order to speak about that tomorrow. I think
it's in the list of the topics we will cover.
Samarium-152, gadolinium-154, and then folks.
So, but some osmiums are also candidates. Now, there are examples I will show for this phase transition here, but that I will discuss in a moment. There are, of course, other variables, like the quadrupole moment. If you go from oblate to prolate, the sign of the quadrupole moment changes, of course. And if you're in between prolate and oblate, so in the gamma unstable region, you cross the quadrupole moment equal to 0. Yeah? So here you have the value 0. It's lying here. So the plot is not in a triangle, it's in a square. Important is to show you the effect of the number of bosons. So this is a realistic calculation with 10 bosons. This is an irrealistic calculation with 40 bosons. And so we can go up to calculations with 100 bosons, and even using the O5 symmetry up to 10,000 bosons. And you see the change in the quadrupole moment becomes sharper, much more sharp, if you increase the number of bosons. Another sensitive signature is a P2 from the second 2 plus to the first 2 plus, and so you see this kind of bird. And so at the prolate oblate, this is increasing enormously, peaking, and then it goes down again. And again, if I do the calculations with 10 bosons, or I do it with 40 bosons, it becomes very short, because there are less quantum fluctuations. Now, So we come to this picture that we have this kind of phase diagram of this very simple Hamiltonian in which we have spherical, prolative form and oblique form, and then we have the symmetries and the first order and second order phase transition. Now, as examples for the prolate oblate and spherical prolate phase transition, we first consider nuclei around platinum-196. Remember, platinum-196 was this example of the O6, which is in between prolate and oblate. Here we have well-defined prolate rotors in hafnium, tungsten, osmium, and so on. And then we continue to the oblate side in the mercury. So, if we plot this on the angle, in fact, it's the extended absolute angle. So then we are moving from well-deformed prolate nuclei over platinum into oblate, small deformed oblate. Now, so what I got here, because it's a little bit difficult to do the calculation, it's in the lower, it's the calculation, because the boson number is changing in every nucleus, you have another boson number. So I plot here the ratio of the 4 to 2 for 10 and 20 bosons. And so you see you go from 3.3 to 2.1 or 2.0. And you have a rapid change at the spherical to deformed transition. And if you look at the quadrupole moment in the prolate-oblate transition, so here was spherical to deformed transition, prolate-oblate transition, then also we'll go from negative quadrupole moments for prolate up to positive quadrupole moments for oblate. And a very sharp transition through zero at the O6 limit. So if we now look at some data, these are samarium nuclei, and we look for the spherical to deformed. So these calculations are now done with the appropriate n numbers, and so we compare the calculation here and the experimental points, and you see very nicely that you can classify the nuclei around. I think these are samarium isotopes. I don't remember exactly. I think this is focus. Anyhow, so you see here at samarium 152 this nucleus which is close to the phase transition. If we look at the osmium to mercury, we clearly in the quadrupole moments have here the negative values, experimental points, the calculation. This is platinum 196, which has not a zero value, but you see that the transition is going sharply through zero a little bit before platinum 196. Maybe at platinum 195.735. That doesn't exist, unfortunately. And then we get here the oblate shapes with still non-zero quadrupole moments for some of the mercury isotopes. Okay. So with that, we close this excursion into shape and phase transitions, on which we will hear more tomorrow by Norbert. And we come now to another subject, which are core excitations. Suppose I have a nucleus close to a closed shell, like cadmium. So in cadmium I have many neutrons, I have many stable isotopes. It's a very nice isotope, 7 stable isotopes, so you can study it very well. And I have below the tin 2 proton holes. Moreover, the stable isotopes are situated near the mid of the neutron shell. That's also important. 114 cadmium is the mid of the neutron shell. Now, because I'm sitting 2 holes below tin, you can imagine that at a certain moment you can have enough energy to move 2 proton particles above the
15 closed shell. Yeah? So then I have 4 holes and 2 particles. Such states exist and are called intruder states. The reason why this is possible energetically is if you now consider this compared, here you have 2 protons and let's say 4 neutrons. In fact, you have much more. And so the neutron-proton interaction is then acting between 2 protons and 4 neutrons, while there you have 6 protons, 4 holes and 2 particles, and the same number of neutrons. And that makes a stronger quadrupole proton-neutron interaction. And that lowers the needed energy for this intruder state. Now, how can we describe that in the interacting boson model? We do that by having an n plus 2 system. So we have a block matrix with n bosons, with Hamiltonian with n bosons, and we have a IBM Hamiltonian with n plus 2 bosons, and of course we have to add a shift in energy. We have to move up these intruder states to higher energy because of the needed energy to make this particle hole excitation. Now, Chris Heide has described microscopically the value of this interaction. So first of all, you need to have actual value of the difference of the particle states in the hole states. This is about 8 MeV, so it's a huge amount. But then you get energy you win back, especially by a quadrupole proton-neutron interaction. And that makes that in the middle of the shell, the intruder states occur at a relatively low excitation energy of about 1 MeV. Then, of course, I have to mix these 2 configurations. And the mixing Hamiltonian is quite simple because it has to be a scalar. Remember, it has to be a scalar. So L equals 0. L equals 0. And then there are 2 combinations. S-decker, S-decker, coupled to 0, and D-decker, D-decker, coupled to 0. We will find out that is more than that in symmetry properties of this interaction. And so I have now alpha and beta as parameters in order to describe this mixing of the normal and the intruder state. Now, first I would like to discuss that new kinds of symmetries are possible. And one is intruder spin or E-spin. So normally we have the IBM, and we describe this as U6 as a standard symmetry. But now we have 2 types of particles. We have particle bosons and we have hole bosons. Yeah? So we can distinguish them by using a concept analog to isospin. So we associate an E-spin with the projection plus 1/2 for the particle bosons and the projection minus 1/2 for the hole bosons. Now if you do the 2 particle 2 hole transformation, then you immediately realize that Ez is conserved in the given nucleus. Yeah? So it means that the general Hamiltonian commutes with the Ez operator equal to 0. And it turns out if you impose some more conditions, you can make Hamiltonians which not only commute with the Z projection of E-spin, but also with E squared. And if they do, then E is a good quantum number. So it means that all states have a given value of E and Ez. So that means you have good intruder spin, and you can now make ladder operators which change particles into holes. This plus change a hole in a particle, and minus change a particle in a hole. And if you now have a Hamiltonian which in addition commutes with this, then you have intruder analog states. And you will describe now different states in different nuclei. So let's take a look at that. So if I start from the thin isotopes, they have 0 particles, 0 holes, yeah, because they are the closed shell. For the protons, I only note here for the protons, 0 particles, 0 holes. So Ez is equal to 0, and then the first excitation is a 2 particle 2 hole, so this gives +1 and -1, but also Ez is equal to 0. But this is E equal 1, and so on. Now, the cadmium isotopes, they have 2 holes, and if I now have the intruder, then, okay, this is -1/2, yeah, because I calculate as bosons. And then I have the 2 particle 4 hole. They also have Ez -1/2, but now E takes the value 3/2. And if I impose intruder analog states, then I can compare the intruder states in cadmium to the normal states in lutetium, because lutetium has 6 holes, and E minus will now reduce the 2 particle to hole, and so we have then a 6 hole state, and Ez projection is -3. I can go over the shell, okay, and I can look at the intruder states in tellurium. So that are the analog states of the intruder states in cadmium, and I can go up to the 6 particle states in barium, which are analog states of the intruder states in cadmium. So you've learned about isospin, but you will learn tomorrow, maybe in the afternoon, about S-spin, which is also SU2 algebra. So you can use the tricks of the symmetries in many different ways. Yeah? So what you do here, in fact, is you have a 2-component system, either proton-neutron, that's isospin, particle-hole, that's E-spin, and we will see neutron-proton boson is F-spin. That comes tomorrow, or in the afternoon. Of course, the important thing is to check whether this is close to reality. So what I show here are the normal states in lutetium, the intruder states in cadmium-114. They start at an energy of 1.1 MeV. Yeah? So I've subtracted all the normal states, and we will show that later, and I look only to the intruder states. And if you compare, it's reasonable. Up to here, there are some larger discrepancies coming up. If I now go to the intruder states in tellurium, they appear at 0.958 MeV. It's less good. Yeah. The agreement is here, but it was much better. And if I go to the barium nucleus with only particles, then we get maybe a better agreement than in tellurium. Of course, there are some doubts. You see this question, these clammers, or how do you call that? Bracket. Parentheses. So it's of course not so easy to identify these intruder states higher in the level scheme. So this is close to 2 MeV. But at least for the first excited state, it's reasonable.
So here, the 0 plus is the second 0 plus excited, right?
No, in fact, it's the third one. I will come to that.
Oh, okay, yeah. So this is just so high energy, so you could allow for this shell jumping.
Yeah. Yeah.
And the particles that jump not one by one, but
because of the pairing. There was a pairing term, and so it's but one particle hole excitation is higher than the 2 particles.
But here you have chosen just such excitations that are okay with that, because we might also have just a single particle jumping. I mean, is this a full level scheme, or you have just chosen some levels that?
No, I will come to that, and you will see how I did that.
Okay.
How your question is, how do I get this?
No, my question is, this is not the full level scheme. This
is not a full level scheme. We will come to that.
Okay.
Now, okay. In fact, the next one. So, I want to illustrate how we do that by considering a case study. And the case study is 112 cadmium. So, as I said before, the cadmium isotopes are unique in several respects. Protons nearly fill the Z50 thin shell. Neutrons are near mid-shell, and in fact there are 8 stable isotopes of cadmium. So this is clearly the mass region where we can learn about nuclear structure. And so one studies we did are fusion evaporation reactions, alpha to N reactions, on palladium populating cadmium-112, and this allowed to establish many multiphonon states up to Nd equals 6. This was also a long time ago. So here you see the comparison. This is an anharmonic rotor where the full lines are fitted states. Yeah? So we fitted excitations up through here. The dashed lines are just non-fitted with extrapolated states. These are experimental spins. They are all determined unique using this reaction. These are the experimental determined states using a simple 4-parameter U5 Hamiltonian. And so you see there is a good agreement of even up to very high excitations. Of course, here you don't see the 2 pluses, or it's only the high spin values which can be identified. Now, how do we come to the intruder states? It's just after doing this bit, we subtract from the total experimental level scheme all these states. And what you keep then is this spectrum. Experimentally, you observe that those which are not described by this fit form a 0 plus, a 2 plus, a 4 plus, a 2 plus, a 0 plus, a 3 plus, a 4 plus, a 6 plus.
Jan, in the previous slide, those ones on the right were left out.
Yeah. Okay. Yeah. So this is the first fit, and then there are some levels of this energy which are not fitted, and I thought they were. The interesting thing is, this looks exactly like an O6 spectrum. Yeah. Remember, in U5 you had 0 to 4, and in O6, as Mark told you, the 0 is higher, and so you have 2, 4. Gamma mistake.
So at what energy is then the 0 plus?
This at 1.1 MeV. Okay. More or less. And so now this was done with a dynamical symmetry fit using U5 with 4 parameters, and now we can fit using 2 parameters in essence because we don't see higher non-sigma max states. The 2 parameters we can fit this spectrum, and that's what you see here. That's the 2 parameter fit of the intruder configuration. And it's reasonable. Only the 4 plus and the 2 plus are not so well reproduced. The rest of the 2 parameters is reasonable. So we see that we have a coexistence of normal states having U5 dynamical symmetry and intruder states having O6 dynamical symmetry. Remember what we learned about partial dynamical symmetry? Both groups, both limits, have O5 as a subgroup. Now, O5 is also defined by boson seniority, so this has to do with the number of boson pairs not coupled to 0. If you look at the Hamiltonian, because it has to be a scalar, you don't change anything of bosons non-coupled to 0 because you create a pair coupled to 0 or you annihilate a pair coupled to 0. S, of course, doesn't change. And so immediately it's clear that this is an O5 scalar. So tensorial character for O5 is 0, like L equals 0 for O3. So that has consequences. Because O5 is a good quantum number, as we saw in the partial dynamical symmetry of both limits. So that means that every state has a definite O5 quantum number. And if I have, let's say, O5 quantum number 2, and I interact with this interaction, then I have to do the vector coupling of 2 and 0 in 5 dimensions. But you can imagine 2 times 0 is 2. So it means that the mixing can only occur between states having the same O5 quantum number. For instance, the ground state has 0, this state has 0. They can mix, but they are so far from that they don't mix. The first excited state here can mix with the first excited state here because they both have O5 quantum number 1. However, this state is very close to another 2 plus state, and so you would expect that it will mix much more strongly with this 2 plus state than with this one. O5 quantum number of this state is 2, and here it's 1, so they cannot mix. They stay pure. And then the 0 pluses here, this is a seniority 0, this was also seniority 0, they can very strongly mix, yeah, due to this selection. Moreover, there is more to the story, because we can determine the tensorial character for O6. Means, remember we had these O6 wave functions before, and so we can now rewrite it. I don't want to do the details using this table. You can rewrite it as the combination of this guy we used before, 2, 0, 0, 0, and 2, 2, 0, 0. Yeah? So again, how to determine the tensorial character, use just the wave functions and plug it in, and then you go to this solution. Now you see that in front of this term, there's a combination of alpha and beta, and in front of this term, there's another combination of alpha and beta. But again, this term, if it acts on an intruder state, it acts on a sigma max state with n minus 2. If you do the annihilation, you cannot change O6 quantum number, and you end up in a nucleus with a different number of bosons. It's the same nucleus in the normal states. They have n bosons and not n plus 2. And because they have n bosons, the maximum value of the O6 quantum number is n. And multiplying n plus 2 with 0, I get n plus 2. These states do not exist in this nucleus. So that means we have kind of effect like in the partial dynamic symmetry, and the mixing Hamiltonian, which is effectively mixing state, is this combination of alpha and beta. This came as a surprise. I have to tell the referee of this letter pointed this out. But it means that instead of having 2 parameters, you have only 1 parameter. Because for any alpha, you can get some kind of different combinations of alpha beta yielding this constant factor. And numerically, you can test that, and it really is true that you have only 1. Now, just give some examples of experiments. One very important thing you can do with cadmium isotopes, because you have 8 stable isotopes, you can do inelastic neutron scattering, N-gamma. And this is very nice because you can vary the energy of the neutron, and the neutron does not feel a Coulomb barrier. Yeah? So even neutrons with energy 0 can enter an atomic nucleus. And so by varying, you can enter in this nucleus, for instance, at 2 MeV, then afterwards at 2.5 MeV, then at 4 MeV, and so on. And so you measure coincidences, and then you know this is only from states below 2 MeV, and then the new states are between 2.5 and 2 MeV, and so on. So it's a very nice and clean method to do complete spectroscopy in atomic nuclei in detail. Moreover, you can measure lifetimes, as shown here, by using kind of ASAM methods. So you can determine lifetimes, you can determine the branching ratios very well, mixing ratios, and so on. And so you can really make complete spectroscopy of cadmium isotopes. So, as an example, let us look at the absolute Be2 values, which were measured for states in cadmium-110. So here it's denoted 1 phonon, 2 phonon, and so for these multi-phonon excitations, you have experimental Be2 values, and if you compare them with the harmonic vibrator, then you have only one which is within the error bars, but the other ones are off. If you compare it with the U5 limit, which has finite n effects, you get a better agreement. If you compare it with U5 plus O6 model, so it includes also effects of the intruders, which will mix in certain states and not mix in other states, the improvement is becoming better. So within the error bar, you're now getting also this guy and this guy. And finally, you can now also do a complete calculation using protons and neutrons degree of freedom, IBM2. Then, of course, you have more parameters and you can improve the description even more. One thing one can test, we can look at 110 cadmium in this kind of U5 SO6 picture. So here we have the 3 phonon states and the absolute Be2 values. Here you have the intruder state and the absolute Be2 values. And you can also describe negative parity states if you include F bosons and P bosons. And so generally up to an energy of about 2 MeV, the agreement is quite good. So finally, of course, let us check what about E-spin. So E-spin gives the prediction that, of course, Be2s have to be the same. And if you look at cadmium, the intruder Be2, and ruthenium, the normal Be2, they are very similar for the different cadmium isotopes. And again, it's not so good if you go over the closed shell to the barium isotopes. There is a large discrepancy. So it seems that the E-spin analog states only hold on one side of the spin. Of course, every dream takes an end, and so the NN prime experiments were continued up to higher energies. So what I showed was up to 2.5 MeV, and so they have been continued to 4 MeV and 3.4 MeV neutrons by Paul Garrett, and part of my group years ago. The analysis took about 15 years. And so you can now extend this in cadmium-112 to much higher energies, up to 3 MeV, and look also, he has also measured all these Be2 values, and then you find out that if you go to the low spin, high phonon states, that the agreement is not good anymore in the Be2s. Yeah? So these are the experimental ones, these are the theoretical ones, and you get quite some discrepancies. But in my point of view, this is of course not so surprising because they are so high in energy.
Jan, what does dashed arrows mean in the lower plot?
These are limits. Yeah. And in fact, 2 minutes too early, so we can have questions. This is the end of my second lecture. So, if there are questions.
Okay.
We have to meet here 1:30.
Yes. So
1:30.
1:30 back. Okay.